Hi, Dylan. Get my ears on. Hi, Dylan.
Hi, Professor P. How are you today?
I'm doing fine. I graded the extra credit.
I saw that.
Oh, you already? All right.
Yeah.
Let's see. Yeah, you did you see the comments on it?
Yeah, that was really helpful actually, because I went back through and I saw how to do it then.
Okay, good. That's great. Dear God, I try and do you guys a break. I try and give you a break and give you an extra time on this thing. And all of a sudden I look in the forum and see there's all kinds of discussions on it.
Oh, really?
Yeah,
Well, they saw an opportunity and they took it.
absolutely. That was my bad. But I've gone in and deleted them. So in any case, Cassidy, Blake, Joe, how are you doing?
Good. What about you?
Peachy keen, wonderful. Just happy to be here.
I'm
You
good.
guys do have a second opportunity to do the extra credit if you would like.
What was the extra
Oh,
credit?
nice.
The extra credit is in a folder. Oh dear God, where's it at now? Okay, let me try and find it. Not launch meeting. Here we go. Okay, I think you access it course content. Are you seeing the screen, guys?
Yep.
Okay, course content and extra credit down here. And extra credit test 2. Okay.
Okay, perfect. Thank you.
It's a Dropbox that basically, please do me one favor. I'm tired of looking at papers like this. Make sure that you orient the papers up and down, not sideways. My neck got creaked. I got a big crick in my neck because of that. Other than that, guys, you also have another attempt at the quiz. I looked at it and really did decide that I didn't get through enough of the material so that you would have known how to do some of those problems. So you have a second attempt at that. Please, while I have your attention here, please do not comment on extra credit, or the quiz is my fault because I opened it up again for you. But please, if something is open, do not comment on it in the forum. It's too easy to get yourselves caught. And then if you get yourselves caught asking questions like that, it's a dead ringer that I'm going to just take the points away. Okay. So please don't comment on those things until the end. All right. A word about the quizzes. Up to this point, you've been pretty much reviewing everything, right, guys? Right?
Yeah.
Yes.
So we've got new material in here. I'm really trying to get you to read ahead, at least look through the PowerPoints to try and give yourself a little bit of foundation. That's why I asked these questions in advance of my going over the material. So please read ahead. All right. Okay, stop sharing. Anybody have any questions about what we did last time? No, I don't want to go there. I want to go here. I believe we ended on the calorimetry thing. Am I correct, guys?
Yep.
This is about where we ended?
Yep.
Okay. Now, if I get through as much material as I did this morning, I'm going to be scrambling to try and get this stuff entered in. I don't want to go too fast, but please bear with me. If you understand something, please tell me right away. Don't let me hanging here, okay? I want to make sure you understand this stuff. I don't necessarily want to go through it real fast, but if I'm not getting that you're not getting this, we're in a whole heap of problems. Okay, guys? So what we're dealing with, when we're dealing with calorimetry, we can't really stick a thermometer in a reaction and get the initial temperature and the final temperature. We can't do that. It's just not possible. So what we have to do is we have to go about it in an indirect manner. That indirect manner is using a constant pressure calorimeter. If we can tell how much the water raises or lowers in its temperature, then we can apply it back to our reaction. Does that make sense to you all? Again,
Yep.
Yep.
thank you. Thank you. So the way we're going to do this is we're going to use the calorimetry equation. This one is important. Q, the heat energy, Q, is equal to the mass of the substance we're dealing with times a constant known as the specific heat times the change in the temperature. Now, you may see this as something referred to as MCAT. It looks like an M, a C, and then a triangle T. The C is nothing more than this same constant as that I'm calling S. There's a reason I call this S and not C. Okay? So you're just going to have to learn my terminology for right now. Now, Dylan, if you were going to make spaghetti for your entire extended family, Dylan, would you need a big pot?
Yeah.
Like a huge pot?
Yeah. I have a lot of family.
Yeah, we're going to talk about 30 gallons, right? Now,
Yeah.
if you're just making macaroni and cheese for yourself, are you going to just grab that 2-quart pot out of your drawer and use that?
Yeah.
So what do you think takes longer to heat up? Your 2-quart
The
pan or that 30-gallon pot?
The 30-gallon pot.
Takes longer, absolutely. So mass has something to do with absorbing heat, absorbing and transferring heat. Okay. Cassidy, you out there, Cassidy?
Yes.
Okay, have you ever cooked with an iron skillet?
No, I have watched that happen though.
Okay, no problem. Then you've seen people take an iron skillet from the burner on top and put it in an oven, right?
Yes.
Would you reach in with your bare hand and grab that iron skillet?
No.
Okay. Now, have you ever cooked something on a piece of aluminum foil, like heated up a piece of pizza or something like that?
Yeah, I currently don't have a toaster, so that's kind of how I make my bagels every
All right.
morning.
All right. Now, when you have that aluminum foil, can you grab it real quick and put it on the stove? And then can you take that foil like a minute or so later and crumple it up?
Yeah.
So the type of substance has something to do with how much heat it absorbs and transfers. Does that make sense, Cassidy?
Yes, it does.
All right, now let's see. Gotta grab another person. Blake, you out there?
Yes.
All right, Blake. Now, you're getting in there for a nice bath, right? And you got the water just perfect so that when you put your little tush in there, everything just relaxes, right? It's at that perfect temperature. It's at bath water temperature, right?
Gotcha.
All right, Blake, do you think it takes more energy to heat your water to bath temperature or to heat it to boiling?
Boiling.
So the temperature change has something to do with the heat. So this is where our entire equation, our heat energy is equal to the mass we're dealing with times the specific heat that has to do something with the substance we're heating, plus the delta T. Delta means change. The final temperature minus the initial temperature. So the amount of energy required to raise the temperature and substance by 1 degree centigrade is its heat capacity. The specific heat deals with a mass that's raised 1 degree Kelvin. So that's the difference between heat capacity and specific heat. And we're going to get into heat capacity a little bit later. So if we deal with the specific heat, it's the heat transferred divided by the mass times the temperature change, or the specific heat times mass times the change in temperature is equal to the heat. All right, let's get into some problems here. Calculate the amount of heat required to heat 105 grams of silver from 10.2 centigrade to 25.8. Blake, you're up here, so I'm going to grab you first.
Okay.
Heat. What does heat stand for in my equation that you see in the little blue box?
Is it joules?
It's
Is that-
joules, but you see the little blue box? It has an
Mhm.
equation there.
Oh, the heat for this would be, I guess, would it be Q or S?
Q.
One of the two.
Q.
Okay, Q.
So what's M?
Is the mass. That's the grams.
That's 105 grams. S.
Mhm.
S is specific heat. You're going to have a little chart
Silver
usually.
is, yep, 0.24 joules per gram, and
And now you got to figure out something. At this point, you've been given two temperatures, and it is important that you put them in the right place.
Gotcha.
What was the final temperature you reached?
25.8 degrees Celsius.
So our final temperature is the 25.8. The initial temperature is 10.2. And that is, it's very, very important that you figure out what your final temperature is and what your initial temperature is. So if I plug all those numbers in, I get 105 times 0.24 times 15.6. I multiply all those numbers up and I get a positive 390 joules. Now, the question said I heated up the silver, did it not?
Yes.
So if I'm heating up the silver, does the silver have more energy after the heating or before the heating?
After.
So if it's after the heating, you notice that the sign is positive. Heat had to be added to the silver to raise its temperature. Is this making sense, ladies and gentlemen?
Yep.
Okay. For instance, what if we used water instead of silver? Remember, we still have the same weight, 105 grams. I'm flipping back between the slides. We still have the same temperature change. But now I've got a different specific heat because I'm dealing with water as opposed to silver. Look how much energy the water jumped. My God, that's almost a 20-ton jump from water to silver. Now let's think about this. Okay? If I have the same amount of energy, we'll just say 1,000 joules out here. Okay? Am I dividing it by a bigger number with water than silver? Guys?
Yes.
Yes.
All right. So if I'm dividing by a bigger number, my mass isn't going to change. Let's just think about your body. Your body mass isn't going to change. Okay? If I'm dividing by a big number here, then doesn't that mean your temperature change is going to be only slight?
Yeah.
That's why water is a magnificent thing That's why our bodies are composed of water. Water has a huge specific heat. That means it can help regulate our body temperatures wonderfully. That's why it's made mostly out of water. Second question. Dylan, you happen to be popping up here. Calculate the final temperature. If 255 grams of 25 centigrade water had 250 kilojoules of energy added to it. Specific heat of water is 4.184. Remember, Q is equal to ms delta T. So what am I going to put in for the Q, Dylan?
255 kilojoules.
That's equal to?
255 grams.
That's the mass times?
4.184 joules per gram.
So we're taking a
C, yeah.
250 times, 250 is equal to 255 times 4.184 times what, Dylan?
The temperature final, which you don't know, subtracted by 25 degrees Celsius.
Fair enough. Problem is set up. We do this math out. Again, be careful of your final and initial temperatures, because what that will do is that will change the sign. It will change the sign of your energy. So be careful about which temperature is the final one and which one is the initial one. I do that solution out and I end up with 250 centigrade. It's so high, this temperature is so high because we're dealing with 25,000 joules of energy. It's a lot of energy that we're adding. All right. Now we got to understand something out. You remember when I was back at one of the first things I said this evening was I said that we had to use water because we can't really measure what the reactions are. And if you remember back to Tuesday, remember we said whatever happens to the system, the opposite thing happens to the surroundings. So if your system is gaining energy, it's got to get that energy from somewhere. What it does is it pulls the energy from the water. If it pulls energy from the water, the temperature goes down. Temperature of the water goes down. If, on the other hand, my system is exothermic, it is releasing energy into the surroundings being the water. As that system is releasing energy, that water is going to go up in temperature because it's accepting the energy that the system is releasing. Does that make sense, guys? Does it make sense? All right, now, the Q of the surroundings is the same in quantity as the Q of the system, but it's opposite in sign. So Q surroundings is equal to negative Q system. Bear that in mind. That's one of the important equations we have to remember. A second one is Q is equal to ms delta T. And there's a third one that's going to come along in calorimetry in a second. What is the specific heat of a 54.234 gram metal bar that's put into boiling water for 20 minutes? Okay, if I put the metal into boiling water for 20 minutes, what's the temperature of the bar?
The temperature of the water?
What is that? It's boiling. It's boiling,
25.
Cassidy.
25.2 degrees Celsius?
Water boils at 25.2 degrees Celsius.
Oh, no, sorry. I was reading a different part of it. I honestly couldn't tell you the boiling point of water. I have
100 degrees Celsius.
Thank you. Thank you, Jackson. Cassidy, that's one that you should know, okay?
Yeah, I just haven't been able to watch Tuesday's lecture yet. So
No, it's just, that's one of the things that you should know. That should be in the back of your mind. Like 12 inches is equal to a foot. Okay? So if the metal bar is in the boiling, and by the way, that was good to understand that it was going to be the temperature of the boiling water. So if it's in the boiling water, we know our initial temperature of our metal is 100 degrees. It weighs 54.234 grams. It's transferred into a calorimeter. The calorimeter has 225 grams of water in it. The initial temperature of the water is 25.2 centigrade. The equilibrium temperature is 27.1 grams. What is the specific heat of the metal? All right, guys, there's only one little bit of information that I haven't put in here, and it's been said over and over again. You're going to use this number so many times, it's going to be memorized. Anybody at this point know what the specific heat of water is?
4.184.
4.184 joules per gram Celsius. So that's another number that you probably should commit to memory. All right. Now, as I said before, we're going to do the heat loss of the metal indirectly by figuring out the heat gain of the water. Do I have the ability to find out how much the water's heat has gained? Do I have the mass of the water? Come on, this is where you say yes. Do I have the mass of the water, guys?
Yes.
Yes.
Do I have the initial temperature of the water?
Yes.
Do I have the final temperature of the water?
Yes.
And do I have the mass?
Yes.
So can I figure out the Q of the water?
Yes.
I do that, I plug it in. I plug it in. I get my 225 times my specific heat of water times my 27.1 minus 25.2. I come up with this number, 1788.66. Now, guys, this is the absolute one time I'm going to tell you to do this because it's so easy to know. Use the rough numbers. Use the rough numbers until you get to the very end of the problem. 99.9% of the time, your significant figures are going to be dictated by the significant figures of the difference of the two temperatures. More than likely, it's going to be 2 or 3. So do the rough figuring out up until the last step. And in the last step, you'll have figured out whether you need 2 or 3 significant figures. Just truncate the number to that and everything will be copacetic. Now, I figured out my water, my heat of my water got heated up 1788.66 joules. Again, remember we said system versus surroundings. Surroundings is equal to negative Q of the system. Our surroundings are our water. So if our water is 1788, then the Q of the metal, our system, is going to be a negative 1788.66. Are we good there?
Yep.
We jumped that bridge, huh? Without a parachute. Anybody ever jumped off a bridge? Your feet get tingly when you're at the very edge. Anyway. So I now know that what my Q of my metal is, right? I just figured it out. Now, the Q of my metal is going to be the mass of my metal times the specific heat of the metal times my final minus my initial temperature of the metal. Let's go back to the original problem. The easy one there. Do we have the mass of the metal?
Yeah.
I just told you we had the Q of the metal. Do we have the final and initial temperatures of the metal?
Yep.
What is it, Blake?
Sorry, I thought that 27.1 was C.
Yes.
Do we? Oh, it
Oh,
is.
no,
Yeah,
it
we
is-
do.
It's, oh, no. So that is a, you're correct.
Cool.
You're absolutely correct. So what's
So
the
yeah,
27.1?
that'd be the final.
Final temperature, good.
Mhm.
You have to understand the final temperature of the water is also going to be the final temperature of whatever you put into the water because they have reached equilibrium. It's like that blacksmith in the old Western movies that takes the horseshoe from the fire pit and throws it in the water and the water steams up. Well, the horseshoe and the water at the very end are at the same temperature. Right now, my metal bar and my water have been risen to 27.1 C. Now, Blake, you said that was the final temperature, correct?
Yes.
What is my initial temperature?
It'd be 25.2.
No, is that the temperature
Oh, we're
of the
looking for
water
the
or the metal?
metal. Ah, gotcha. I guess you'd have to do separate calculations for that.
We've already, where was the metal at before it got put in the water?
Let's see. Oh, boiling water, 100 degrees Celsius. Gotcha.
So the initial temperature was 100 degrees. Now the key is, guys, I'm gonna go back here. Remember, when we changed the sign of the heat from the water to be negative because we were translating it into the Q of the metal, when we go and figure out the metal, our final temperature is less than our initial temperature. So this negative is going to cancel out the other negative. I plug my things in here. I get 1788.66, negative 1788.66 is equal to 54.234 times the specific heat, what I'm solving for, times 27.1 minus 100. I do that math out and I end up with 45.45 joules per gram Celsius. Now, interestingly enough, that's one of those things that we can look into a chart like this, see, specific heat for iron is 0.45. That must mean we had iron. That was the metal. Questions, guys? Are we good with this?
Yes.
We're okay? Everything is making sense? I'm not saying anything stupid.
Yeah, I get it.
All
I
right.
think so.
All right. Just a quick question. Let's see, who am I going to bother? Joe. You there, Joe?
Yeah, what's up?
If you take 6,500 kilojoules of energy away from a pool, does the temperature go up or does it go down?
Down.
Yes. Be confident, Joe. You're taking
Down.
energy away from the pool. So if you're taking energy away, that must mean the temperature has to go down. Okay, well, I got you there, Joe. Have you ever used a thermos in your life?
No.
Never? Has anybody out there used a thermos in their lifetime?
Yes.
Yes.
Does the coffee stay warm forever?
No.
Why not, Cassidy?
I don't know. I guess it also like depends on what kind of bottle you have and you open it to drink your coffee, so then heat escapes in that way over time.
Okay, I can buy. I can buy that if you take the top off, it would somewhat go out, heat would go out that way. But even if, Cassidy, even if you keep that lid on very, very tight, eventually the coffee would cool to room temperature. Why? How can this happen? Thermoses are supposed to keep things hot.
I honestly could not explain that one for you. I have like a thought in my head, but I know if I tried to translate it, it would not make any sense at all.
Give it a shot.
Give
Give it a shot.
I definitely feel like it has to do with whatever kind of material the thermos is like made with to see how long it stays warm, and then some kind
Okay.
of like heat transfer.
Go ahead. Go ahead. Does the
That's about where
thermos-
the thought train ended in my mind, honestly.
Does the thermos itself absorb heat?
Yes.
If the thermos is absorbing heat, it's absorbing heat from the hot liquid, right?
Yes.
So eventually the hot liquid gets cooled because the thermos is absorbing some of that heat. So we now have two things we have to deal with. We have to realize that the water is gaining energy. The surrounding water is gaining energy. But also at this same time, whatever we're doing this experiment in is also absorbing some of that energy. So that the total energy that is done by the system, the total energy that is expended by the system is going to be equal to the energy of the water plus the energy absorbed by the calorimeter. And we have a second formula. The heat absorbed by the calorimeter is equal to the calorimeter constant, which is a C, times the change in temperature. And note, when you're doing this, the temperature change for the calorimeter is the same as the water's temperature change. Because like the water, it's undergoing that same temperature change. So your total heat of your system is going to be the ms delta T for the water plus the C delta T for your calorimeter. And now you understand why I chose to use S as opposed to C. I didn't want to confuse the issue at this juncture. So the total heat that the system either absorbs or expels, that total heat of the system is going to be equal to the heat of the water determined from ms delta T and the heat absorbed by the calorimeter, which is C delta T. And the hard part to understand is that the temperature of the water change and the temperature of the calorimeter change is the same. So you're going to get problems like this with a whole bunch of numbers in them, and you got to wade through the numbers. Just like in the last problem we had, I have a metal pellet that weighed 52.1 grams. That metal pellet was originally at 79.8 Celsius. It was dropped into a calorimeter. The calorimeter contained 125 grams of water, initially at 25.1 Celsius. The final temperature at equilibrium was 28.3. The heat capacity of the calorimeter is 45.2. Calculate the specific heat. So this problem is just the same as the last one we solved. The only thing I'm doing is I'm introducing another term here, and that is the calorimetry constant and the change in temperature, so that we get the energy absorbed by the calorimeter. So if I'm going to do this, again, Q system is going to be equal to negative Q surroundings. Only the surroundings have two components. The surroundings are the water and the heat absorbed by the calorimeter. So I know that my Q total for the system is going to be the MS delta T, 125 times 4.184 times final temperature minus initial temperature, plus I've got this other factor out here. My calorimetry constant is 45.2, and I'm using the same delta T as I did for the water. I add these two up. I got 1673 and 140. I add those up. I get 1813 joules for both the for the surroundings, that is the water and the calorimeter. Again, my surroundings are minus Q of the system. So my Q of my system, the Q of the metal, is negative 1813 joules. Next, I just plug it into my metal equation. Now, you got to be careful, guys. You got to be careful that you add the mass of the water where it's supposed to go and the mass of the metal where it's supposed to go. The metal, the water, I believe, was 125 grams. But now we're dealing with the Q of the metal, so we're going to use the 52.1 grams. So that's the mass of the metal. We're trying to figure out the specific heat. Our final temperature, again, was the equilibrium temperature that the water came to. It was to 28.3 Celsius. Initial temperature was 79.8. I plug that in there. Remember, this is going to be a negative number. This is a negative number. They cancel out. My specific heat is going to be positive, a positive 0.68 joules per gram Celsius. How are we doing so far? We doing
Good.
okay?
Good.
Okay. Just like anything else in life, once you get comfortable, somebody throws something else in the mix to make you uncomfortable. Okay. We are going to calculate the change in enthalpy. Change in enthalpy is delta H. We'll learn about that again later. That is usually in kilojoules per mole. When 0.751 grams of ammonium chloride are dissolved in a constant pressure calorimeter with a heat capacity of 37.1 joules per centigrade. The calorimeter contains 100 grams of water at 25 C. Final temperature after dissolving the compound is 19.3. Okay, Ian, you feel up to this?
Somewhat.
Okay. Do I have the mass, specific heat, and change in water temperature?
Yes.
Okay. So I can figure out how much energy was transferred to the water, right?
Right.
Do I
Wait,
have the calorimeter constant, and do I have the change in the temperature of the water?
You have the change in temp for the water. What would the calorimeter constant be? I hopped into the Zoom call late. I missed the first part.
It's heat capacity.
Okay, so yes.
So we have both. So not only do we have the ability to determine the heat absorbed by the water, we also have the ability to determine the heat absorbed by the calorimeter? Ian, do you know, how am I going to get the heat of the water? Tell me the numbers.
The initial versus the final. So it'd be
What's my final temperature?
19.3 degrees C,
Minus?
25 degrees C.
Ooh, we have something different here. My final temperature went down. So the water's going to be losing energy because the temperature went down. So you have 19.3 minus 25. What else do you have, Ian?
The weight of the ammonium chloride and then the amount of water.
Okay,
Weight of
what
the
am I
water.
going to use? Am I going to use the weight of the ammonium chloride, or am I going to use the weight of the water? And let me ask you
Water.
one more question. What are we determining the temperature change of? Are we determining the temperature change of the water or the ammonium chloride?
Wouldn't it be water?
Yeah, absolutely. So if we're using the temperature change of the water, which mass am I going to use? The 100 grams?
100 grams of water.
We're going to use the 100 grams of water. We're going to take our 100 grams of water times the specific heat, which is 4.814, times 19.3 minus 25. To that whole big number, we're going to add, Ian, you've been here for a while. Let me ask somebody else. Jackson, part of the heat that gets absorbed is from the water. Where else does the heat get absorbed from?
Calorimeter.
So what are we going to do to get the heat absorbed by the calorimeter?
The heat capacity times the temperature change.
So I'm going to put all that together. My Q surroundings is equal to negative Q system. My surroundings is equal to 100 times 4.184 times 19.3 minus 25 plus the heat capacity, 37.1 times 19.3 minus 25. I add all that up. Notice the Q of my surroundings is a negative number. That means that my Q of my system is going to be a positive number. So, was my system endothermic or exothermic? Did my system gain energy or did it lose energy? Is the sign associated with the Q system positive or negative?
Positive.
It's positive. If the sign is positive, then it's gained energy. If it's gained energy, it's endothermic. So I have negative 2595 joules. I believe the question wanted it in kilojoules. So I multiply that by 1 kilojoule over 1,000 joules, and I get 2.595 kilojoules is the Q of my system. My system being the dissolution of the ammonium chloride in water. Now, I need to go back to my original problem, if I can find it. I want the change in enthalpy, kilojoules per mole. I have the weight of my substance that's being dissolved. Can I get moles of my ammonium chloride?
Yes.
Yes.
So if I can get moles of my ammonium chloride, then all I'm going to do is take the heat that was caused by 0.751 grams. I'm going to take that heat and divide this heat by the amount of moles I have. And that will give me kilojoules per mole. So that's the molar mass of ammonium chloride. I divide that into my 0.751 to get the number of moles. And I just take the kilojoules of heat divided by that amount of moles. And I get the enthalpy of the dissolution of ammonium chloride. Are we okay, guys? Are we okay?
Yes.
Yes.
Okay, this is a similar problem to one we've done before. If you want to look at it, go for it. And okay, I want to point out this problem. Do you see this last line? Am I going to have to do a C delta T with this particular problem?
No.
No, because I'm assuming that the heat loss to the calorimeter is 0. When I say that the heat loss is negligible, I'm assuming that that heat is 0, so I don't have to worry about it. Okay. I'm going to do one more of these type problems. Okay. I just had to look there and see what was going on. All right. What is the limiting reagent? If I have 25 milliliters of 1.25 molar HBr and 25 milliliters of 1.25 molar ammonium hydroxide, what is my limiting reagent? You don't need a calculator, guys.
Are they even?
They're even. They're even. So remember what we were saying when we were determining the heat of the reaction. We have to employ the coefficients. All right. Now, is 25 milliliters times 1.25 molar, is that going to end up being 1 mole? Come on, guys, this is an easy question. Is 25 milliliters times 1.25 molar, is that going to give me 1 mole's worth of HBr?
Yeah, but wouldn't it be 1,000?
No, it's not going to.
Oh, okay.
You're multiplying the liters of the HBr times the concentration. So you're going to take liters of the 25, which is going to be 0.025 liters times 1.25. You're not anywhere close. You're somewhere around 0.43 moles. Right, Blake? You see where I'm coming?
Would you divide it?
Eventually, we're going to do.
Oh, okay.
What we're going to do is we're going to figure out the heat caused by this reaction. We're going to figure out that heat by figuring out how much the water temperature increases and how much the calorimeter absorbs. That will give us the total heat expended by this reaction. Then we are going to take the total heat expended by the reaction, figure out how many moles we have, and we're going to take that total heat and divide it by the number of moles. That's going to give us our enthalpy of reaction in kilojoules per mole. That's how we're doing this particular problem. Okay, so I'm looking at this. What is the total volume? What's the total volume that's been added to my calorimeter?
50 milliliter.
50 milliliters. So we're going to use the 50 milliliters as the mass of the water solution that's being heated up. So 50 grams. We're going to assume that the density of the solution is 1 gram per milliliter. 50 milliliters times 1 gram gives me 50 grams. Now, do I know what the heat capacity of water is?
Yes.
4.184. Start to remember it, guys. I'm going to get sick and tired of saying it. Do I also know what my initial temperature is and what my final temperature is?
Yes.
And I got to see where that's at. Oh, yeah. So when I do this problem, my Q of my water is going to be 50 grams times 4.184 times 32.0 minus 25. That's the Q, not of water, but of my surroundings. To that, I'm going to add my calorimetry constant, which is 170 joules per C, again, times the 32 minus 25. Positive numbers. So my Q surrounding is going to be, my Q surroundings is going to be 464 plus 1190. Notice the calorimeter absorbed a whole lot more than the water did. So I add those two together, I get 2654 joules, which equals 2.654 kilojoules. Q of surroundings equals negative the Q of my system. In this case, my system is the reaction that's occurring. My reaction is the thing that's creating the heat. So that is my system. So I get negative 2.654 kilojoules. Now, this is the hard part to understand. When we were doing the heat absorbed by the water, we added the volume of the HBr and we added the volume of the ammonium hydroxide, right, guys? Right?
Yes.
When we're dividing it by the moles, we're going to divide it by only the limiting reagent. Because if you remember, when we were doing those heats of reaction and multiplying them by the moles or dividing them by the moles, the only thing we did was we used the coefficient. In this case, the coefficients are 1 to 1. So I'm going to take my Q of reaction and I'm going to figure out how many moles of my limiting reagent. They both limit one another. So I'm going to take my 0.02500 liters times 1.25 molar, and I'm going to get 0.0313 moles. I divide my reaction Q by the moles contributed by my limiting reagent. This gives me a Q of reaction, a delta H of reaction of negative 84.9 kilojoules per mole. Are we doing fine, guys?
I have a question.
Yeah, Joe.
So my internet went out. I didn't see, where did the 50 grams come from?
Okay. Now, I put 25 milliliters of HBr in this calorimeter. I also put 25 milliliters of my NH4OH in there. Okay? So that when I measured the temperature, I was measuring the temperature change of all 50 milliliters. Did that make sense to you, Joe?
Okay, yeah, I get it now. Okay.
And then I was just using a simple 1 gram per milliliter conversion, a density of 1 gram per milliliter to go from milliliters into grams. Now, at the very end of this, when I'm trying to figure out my kilojoules per mole, I'm going to only use one of them because I'm going to be using the limiting reagent. I can choose one or the other. It doesn't really matter. I'm just going to get the limiting reagent number of moles, divide that into the Q of the reaction. That will be my enthalpy. Anything else, guys? Wow, we're about 10 slides ahead of the morning. And continuing on. Okay. We can work backwards too. We can work backwards in this determination. All right. I've given you my enthalpy of my reaction. That's 56.2 kilojoules per mole. I've also given you 75 milliliters of 0.9 molar HCl and 75 milliliters of 0.9 NaOH. Again, we do not have a limiting reagent, or they're both limiting one another. So in order to figure out the number of moles, we're going to take the 0.07500 times 0.9, and that's going to give us 0.0675 moles. So the first step I'm going to do is I'm going to take my 0.675 moles, multiply that by my heat of reaction, my enthalpy. This gives me that this reaction should produce 3.79 kilojoules of energy. Again, this should be a negative because my enthalpy was a negative. So that should be a negative. And this should be a negative. All right. So negative my heat of reaction is equal to Q of my water. Therefore, the Q of my water is equal to 3.79 kilojoules. I change that into joules by multiplying it by 1,000 joules over 1 kilojoule. I end up with 3,790 joules. Now remember, the mass of the liquid that was heated is going to be the mass of both solutions. So I have 75 milliliters and 75 milliliters, 150 milliliters. This time, I have told you to assume that the density was 1.02. So that gives me 153 grams of my solution. At this point, I know what my Q of my water is. I know what my mass of my water is, the specific heat, and this gave me the difference in temperatures. So I'm going to plug in my final temperature and initial temperature. C, we don't know. We're solving for C. Temperature final and temperature initial are going to be the same as there. I end up doing the math out, and my calorimetry constant turns out to be 330 joules per centigrade. Done a lot of calorimetry problems, guys. Questions on them? Please, 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 please do the extra homework. The extra homework is much better at doing problems like this than the MyLab and Mastering is. So please do the extra homework. It's going to help you. Got a few more minutes here, so let's go through few more things, and then we'll call it an evening. Okay. Reactions can be carried out in what is called a bomb calorimeter. And basically what a bomb calorimeter is you are actually exploding something. You have an outside container that is filled with water. And you have a chamber that's inside of this water-filled chamber. What they do is they put pure oxygen in on this object that's in this container, and they spark it. It blows up, much like if you had a propane tank and you lit it, it would blow up. Only the thing is, it creates a whole bunch of energy, and it dissipates that energy to the liquid around it, and we're able to measure the temperature before and after. The difference is, this is not a constant pressure apparatus. This is considered a constant volume apparatus. So, when we are determining our energy change, we are determining the change in energy, not enthalpy. It's a semantic thing, but usually for most reactions, the difference between enthalpy and change in energy is minuscule. But you just have to know that in bomb calorimetry, we're measuring the energy change, not the enthalpy. Constant pressure, we're measuring the enthalpy. So, if we put a known amount of something in the calorimeter, we can determine the Q by doing ms delta T, then divide by the moles to get the enthalpy. This is how they determine how many calories a walnut has. Or they'll put a Fruit Loop into one of these chambers and determine how many calories that Fruit Loop has. Do I need to go through one more of these problems, or can I venture on, guys? Are we
You go through
okay,
one
or do you
more.
need another problem?
Could you do one more?
Happy to. Just happen to have it up here. Who's that? Dylan? Who asked me for the other one?
Me.
There were two of them.
Ian?
Yeah.
Okay, Ian, good. You're going to do this. My calorimeter had 95 grams of water in it. And the temperature went from 19.5 C to 26.8 C. What is the caloric value in kilocalories per gram? So all we're doing here, Ian, is we're figuring out what the Q is. Once we figure out what the Q is, then all we're going to have to do is divide it by the 0.11 grams.
Okay.
That's all we're doing. So you tell me, how do I figure out what my Q of my water is?
Was this the last problem we just did?
Similar problem.
Okay.
Do I have the mass of water in?
Yes.
What is
And
it?
you got the change. 95 grams.
Okay,
And then-
we're going to do one slight difference here. Since we want kilocalories, instead of using the 4.184 joules per gram Celsius, we're going to use another specific heat, which is 1 calorie per gram Celsius. Okay? And we're
Okay.
doing that just simply because the final answer wants to be in kilocalories. Okay, did that
So
make
we-
sense, Ian?
Yeah. We don't have to convert the 95 grams then, do we? Or-
Nope.
Okay.
So tell me what numbers I'm putting in my expression.
You'd put 95 grams for the weight of water, and then
Times?
once you do the 19.5 C minus 26.8 C,
What was my final temperature?
26.8.
So my final
Oh.
temperature minus the initial temperature.
Okay, I did that backwards.
Mhm.
26.8 minus 19.5.
That's what I'm telling you, Ian. You got to be careful about where you put the final and initial temperatures.
Got it.
Okay. Now, what's the specific heat of water? What did I tell you I wanted you to use? Something about calories?
Yeah, kilocalories per.
Nope. The specific heat's going to be in calories.
Oh,
It's
I
a
didn't write
number
that.
between 0 and 2, Ian.
Isn't it
Somewhere
0,
between 0.9 and 1.1, Ian.
1?
There we go.
My bad.
So you're going to multiply 95 grams times 1 calorie per gram Celsius times 26.8 minus 19.5. And you're going to come up with, we do this math out, we come up with 2,900 joules. That is my surroundings. We're assuming that the calorimeter did not absorb any heat. So that's my surroundings. In order to get my system, the Q of the nut, I have to take my Q of water and make it negative. I wanted this answer in kilojoules per gram. So I have to take the 2,900 joules, multiply it by 1 kilogram over 1,000 joules. This gives me 2.9 kilograms. And remember what we said we were going to do with the last step, Ian.
Was that the 1 kcal per GC?
Nope, we're going to turn it. We just, why did I do this? Sorry. I do stupid things at times. 26.8 minus 19.5. 26.8 minus 19.5 times 95 equals 693. So I got to change this into thank you. I got to change this into new slide. The only thing I have now to do is this is the kcalories of my reaction, but my kcalories involved only 0.11 grams of the nut. So I'm going to take my kcalories and divide it by 0.11. No! Dear God, I hate computers.
That would be
Thank
a
you.
-2, right?
Yes.
Would it be -0.6935?
Hmm?
But 693.
You mean up here?
Wouldn't that be the
Yep.
same?
We end up with 6.3 kcalories per gram. Again, this is a suggestion for you. Use the rough calculations until you get to the very end. This ensures that I'm only going to have 2 significant figures. This number here is 2 sig figs. Just wait till the very end to do your final truncating of the numbers. This is as good a place as any to finish for the evening. We got through all the calorimetry problems today, guys. Dynamite. I've got to go through Hess's Law, and that's going to entail about another 30 some slides. And after that, we're going to head on into quantum mechanics. Quantum mechanics is not the same thing as you were introduced to in intro. This is going to be much more in depth. Do I have any questions about this?
Will this video be up on the Zoom lecture, or will it be the morning one?
They both should be up.
Okay.
Ian, I'm sorry if I missed every now and again. What happens is it takes so long for these things to load up that I get lost in the middle of them. And so eventually they do get loaded up. For example, I can show you what's in there now. Let's see. I don't want this. I want this. Why do computers do what you tell them to do rather than what you want them to do? Okay. All right, Ian, I'm in the class right now, okay? If we look, we go down to the Zoom meetings. If you look at the morning class,
Okay.
if you look at the morning class, that's even complete for the whole thing. And it's just-
Okay.
I managed to load this up this morning. You see?
Yeah.
I got the dates, and
All right.
I started doing something smart later on, which was I started putting titles on these as well. So at least you
All right.
have that. Okay.
Thank you.
Anything else? Anybody else has? Oh, Ian,
Yeah.
look at the video in the online outline as well.
Okay. Yeah, I started doing that. I did that for the quiz.
Okay. Try and do that as well. That will help. That will help you.
Okay. Thank you.
You're welcome. Anybody have anything else, guys? Okay, nothing else. I will see you later. This will be loaded up and in there come the end of the night tonight.
Thank you. Have a good weekend.
You take care. You have a good weekend too, Cassidy.
Have a good weekend.
You
Thank
too.
you.
Have a good one.
See ya.
Bye. See you later. Oh, I got down to one real quick here.